Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so as I promised, so I would like to show or to explain how to draw a shear force diagram and bending moment diagram based on example 12.1, example 12.1 Hibbeler, okay, under topic moment distribution method. Okay, actually this example I have discussed in class. This is the continuous beam A and D are fixed. Okay, and after doing moment distribution, okay, we have actually got the end moment, okay, as stated. End moment as stated. So we find that MAB is positive 62.625. Okay, and then MBA is 125.248, and then MBC is negative 125.248, and next MCB is 281.575, MCD is negative 281.575, and then last value is MDC is equal to 234.258. Okay, so this is end moment, member end moment, the output that we get from table, from distribution table when we analyze structure, when we analyze beam using moment distribution method. And this member end moment is actually the end moment. The end moment is actually the internal moment. So this is internal moments. So what does it mean? This internal moment means that this is internal forces. Okay, this is internal forces, internal moment is internal forces in the beam, and from this internal moment we should draw the bending moment diagram. Okay, basically from the moment sign, from the moment direction that we get, we can sketch, okay, the bending moment diagram directly. For example, we just need to look at to the sign for each moment that we get. Okay, MAB, it is positive. So it is positive, so we have to put positive direction for AB. And then we get another positive, this is positive direction. And then for BC, we get negative. So this is negative direction. Okay, and then for CB, we get positive. So this is positive direction. For CD, negative. This is negative direction. And for DC, this is positive. So this is positive direction. So what does it mean? This negative positive direction shows the moment position in the bending moment diagram. The moment position in the bending moment diagram. The first and the last moment position. So we get, so for AB we get this point and this point. So we just need to join all the dots, start from 0 and at 0. So we just need to join the line, the dot. Then we get the BMD for A and B. And then for BC, the first position of course is 0 position. This is 0 position. And then the second position, and then this is the other position, and the last position must be back, must be back to 0, because the concept of a shear force diagram as well as bending moment diagram, the diagram must be started at 0 and end at 0. So what we need to do is only join all the dot. However, for UDL, we know that from for UDL, we will get curve line for BMD. So the maximum normally in UDL in UDL, we may have maximum moment in the bending moment diagram. Maximum moment in the bending moment diagram, for example, this. Okay, if the diagram has maximum moment, means that there is intersection in the shear force diagram. So this is the shear force diagram. Okay, but we cannot confirm this if we don't draw shear force diagram. So we have to draw shear force diagram in order to identify the point. Okay, the maximum point, the maximum moment in the diagram. Okay, if for example the shear force diagram, we just get, okay, this is shear force diagram. This is also shear force diagram. Okay, if in the shear force diagram, after doing calculation, if shear force diagram, we just get trapezium, so we don't have maximum moment. Okay, trapezium, if we get trapezium, trapezium means no maximum moment. No maximum moment. We will have maximum moment whenever we have intersection in the shear force diagram. So today, I will show to you how we can determine the value in this diagram. Okay, the value in this diagram as well as this diagram. Okay, this will be B and C, and then this is C and D, because AB is now settled. Okay, AB, the value is 62.625. This is 62.625, and this is 125.248. This is positive, negative. So AB settled. AB settled. Now we want to focus on beam BC in order to identify whether it has maximum moment. Okay, and what is the value of maximum moment. Okay, and then we will continue to calculate the maximum moment for member CD. Because member CD is subjected to to point load at the center. Okay, so let's do it right now. So we start like this. Okay, we get MAB is 62.625. MBA is 125.248. 125.248. This is AB. And then we get MBA equal to negative 125.248. And MBC is 281.575. Is 281.575. MCB we get negative 281.575, and MCD is equal to 234.258. 234.258. Okay, now. Okay, so I want to focus on these two, because we will now determine maximum moment in member BC and CD. Okay, so what we need to do is we will draw the free body diagram for member BC. Okay, the free body diagram for member BC. So we draw member BC. Member BC is subjected by UDL, and then under member BC, we will have BY. Okay, this is BY2, this is CY1. Okay, the label. So we have moment. Moment is negative 125. The moment is 125.28. 248, and then we get 281.575. Okay, the UDL is 20 and length is 12. UDL is 20 and this is 12 meter, kilonewton per meter. Okay, so this is B and C. Okay, means that we have to analyze this beam. We need to calculate BY2 and CY1. This is the label for BY. Okay, why it is BY2 and CY1? Because the original diagram, if we draw the diagram in full like this, okay, we will have this one as AY, this one as BY1, this is BY2, this is CY1, CY2 and DY. Okay, now we are calculating this. So that's why it is BY2 and CY1, because BY is actually BY1 plus BY2. So all this has been discussed, as I mentioned, under chapter number 11, slope deflection method. Same goes to CY. CY is equal to CY1 plus CY2. Okay, so now we are now considering member BC, so that is why we have this label. We have this label and this label. So we will analyze this just like we analyze simply supported beam by using equilibrium equation. Okay, using equilibrium equation, using equilibrium equation, using equilibrium equation, using equilibrium equation, we will determine the value of BY2 and value of CY1. Okay, so we are going to analyze this beam or beam BC by using equilibrium equation to calculate BY2 and CY1. Okay, so we will take moment at B, so we will get negative 125.248, okay, plus 281.575, okay, plus 20 times 12 times 6 minus 12 CY1 equal to 0. So we need to calculate this. We need to calculate this CY1. CY1. Okay, so we need to calculate CY1. Okay, CY1. So forget to bring my calculator. So let's find calculator. Fx. Okay. Okay, let's now calculate the value. So it is negative 125, negative 125.248. Okay, plus 281.575. Okay, plus with 20 times 12 times 6. Okay, equal to this, and we divide by 12. We divide by 12. So we get 133.0.027. We get 133.027 kilonewton. Kilonewton. Okay, 133.027 kilonewton. So from this, we will continue to identify BY2. So by taking total Fy is equal to 0. Total Fy is equal to 0. So we get 20 times 12. Okay, plus BY2 plus 133.027 equal to 0. So we will get BY2 is equal to minus ya, minus. So we get okay, it is 240 minus 133.027 equal 106.973. So this is 106.973. This is kilonewton. Okay, kilonewton. So this is the shear value. The shear value. So from this, okay, from this value, so now we will draw the BMD. Sorry, the shear force diagram. The shear force diagram. Shear force diagram. Okay, so BY is 106. BY is 106.93973. So it is like this. This is 106.973. Okay, minus 240, we get CY1 here, somewhere here. So this is 133.027. Okay, so what we get? So we get the intersection. We get the intersection. Okay, so let's do it by ruler. So it is like this. Okay, by is positive, so we get this. And then cy is negative 133. And then there is an intersection. There is an intersection in the shear force diagram. So this is shear force diagram. Shear force diagram. So this will be positive side, this will be negative side. Negative. Okay, so the idea of doing this is like this. Shear force diagram or bending moment diagram, we must know that the diagram must close loop. Means that it will be started at this position, zero position actually, and then go to this position, and then go to this position. And when we have this negative 133.027, we need to plus back with cy. We need to plus back with this cy so that this point will move back to 0 point. Okay, means that it will actually start from, okay, the direction is like this. Okay, the direction is like this, the flow. Okay, it's like this. So the first point is this point, the last point is this point. Okay, so this is the first point, this is last point, and there is an intersection. There is an intersection. So this intersection, how we determine this length, okay, is actually very simple. Okay, it is very simple actually. How we get this length? This is equal to, okay, this length. Okay, this length as well as this length. How we are going to determine this length? This is actually equal to 106.973 divided by 12. And this is equal to 106 106.973, we divide by 12. It is 8.91. This is 8.91 meter. Okay, we can also check back this. Okay, the length. So it is, wait. It is 12 or divide by 106 or 106 divide by, okay. We check back with the unit. So it is kilonewton divide by 12 is length, not 12. It is divide by W. W is 20. Sorry, W is 20. So we divide by 20. Okay, why we divide by 20? Because it is kilonewton divide by kilonewton per meter. Okay, because this one, this is okay, this is the shear force. The shear force in kilonewton we divide by W. This is W, and the unit is kilonewton per meter. So we will get the unit meter. Okay, unit meter. So so it's not divided by 12. 12 is length, sorry. So we have to divide by W. We have to divide by W. So this is W. So 106.973. Again, we calculate the value. 106. 106.973. 0.973. We divide by 20. it is 5.349. 5.35 doesn't matter. 5.35. It is 5. This is 5.35 meter. 5.35 meter. So the remaining it is 12 minus 5.35, or we can also get from 133.133.027 divided by W. So divide by W. Okay, divide by W, we should get back total is 12. It is 133.027. It is 133.027. We divide by 20. We get 6.65. It is 6.65. So this one is 6.65 meter. And the total equal to 12. 6.65. 6.65 plus 5.35. So we get 12. Okay, so now we have calculate the distance. The distance means that the intersection position. So now from this we will draw the bending moment diagram, and then we can calculate the maximum moment. So how we are going to do this? Okay, so let's say, okay, now we draw the line for bending moment diagram. The bending moment diagram. So the value is 125.248. 125.248. And it is 281, if I'm not mistaken. 281.578. 281.578. This is 125.248. 248. So now we have to calculate the area of this. Okay, the area of this. The area. So the area of this is equal to, it is 106.973 times 5.35. Okay, divide by 2. Okay, the area is 286.153. 286.153. The area is 286.153. 286.153. 286.153. So means that, and the sign is positive. Okay, the sign is positive. So we have to plus, means plus. So it is 125.248. 125.248. We have to plus the area. Okay, it means that it is 125.248. We have to plus with 286.153. Okay, let's check. One two 5.248. One two 5.248. 125.248. We have to plus with, okay, let's check first, yeah. 286.153. Wait, we minus by 6.65 times 133.027 times 0.5. Check. Negative 125.248, okay, plus 286.153 minus 6.65 times 133.027 times 0.5. Okay. Okay, so the maximum moment is actually equal to how to get maximum moment. Okay, maximum moment equal to negative 125.248. We have to plus with area of the first rectangular 1/2 times 106.973 106.973 times with 5.35. Okay, this is equal to again negative 125.248. Okay, we have to plus times 106.973. We get 160. So it is 160.905 kilonewton meter. So means that this is actually the maximum moment. This is the maximum moment somewhere here at distance 5.35. At distance 5.35, it is actually located here, and the value is 1 160.905. Okay, so this is the, we just need to join this line. Okay, so what we get is like this. Means that, okay, this is the BMD. Okay, this is the maximum moment. Maximum moment. So this is for member BC. This is for member BC. Okay, to check back, we can continue actually. We can continue to check back. Okay, for checking. Okay, for checking. Okay, we continue. We just need to continue 160. It is 160.905. We have to minus the area of second one, second triangular. It is 126.65, 6.65, and 133.027. 133.027, and we should get 281. Okay, 281. So this will equal to 281.6. Okay, so just check, and we should get this value. Okay, so let's check. 160. Okay, 281.4, doesn't matter because of decimal places only. So we get 4 here from calculator. I calculate this is 4, but doesn't matter. This is just for decimal places only. So this is correct. This is correct. So this is the correct bending moment diagram for member BC. For member BC. Okay, so we can actually do the same for member CD. For member CD. Okay, for member CD. Okay, let's continue with member CD. Okay, for member CD. For member CD, we have this. We have point load. Okay, so we have this shear. It is 4 meter. 4 meter. And it is 250 kilonewton. And the moment is 281.575 and 234.258. 258. So this is CD. So this will be CY2 and DY. So by using equilibrium equation, again, just like we analyze simply supported beam, so we will calculate taking moment at C is equal to 0. So it's negative 281.575. Okay, plus with 234.258 plus 250 times 4 minus 8 dy. So dy is equal to, it is negative 281.575 plus 234.258 plus 250 times 4, and we divide by 8. So we get 119.085. 119.085. 119.085 kilonewton dy. Okay. And then we apply total Fy is equal to 0. So what we get is Cy2 is equal to 250 minus 119.085. So it is equal to 130.915. 130.915. 130.915 kilonewton. Okay. So for the diagram, we get like this. Okay, we get like this. And then go straight 4 meter length, and then we get this. And then we get this. And this. Okay. Close the loop. So it is positive. It is positive. It is negative. This is C and D. C and D. So this is 4 meter. Okay, the value is 130. This is 130.915 and 119.085. So this is the shear force diagram. Shear force diagram. And for bending moment diagram, again, bending moment diagram is the area of shear force diagram. So it's quite simple compared to UDL. It is like this. The first point, the first moment is 281.575. 281.575. Okay, it is 281.575 here, and 234.258. This 234. And okay, the intersection should be equal to this actually. Okay, so the maximum moment will be located on this line. Okay, the previous also like this. Okay, so it is, This is 234. This is 234. This is 281. 234, 575. 575 and 234.258. 258. So we have to plus the area. It is negative 234.575 plus 130.915 times 4. We get 289. 289. This is 289.085. 085. And we minus by the other rectangular. We minus by 234 times 4. 234.258 times 4. Is 289.085 minus 119.085 times 4. Okay. 281.575 plus area 130.915 times 4. 281.575 plus 4 times 130.915. Sorry, wrong value. Okay, should be 242.085. 242.085. Check back. Okay, we have to minus the area of this. We have to minus by 4 times 119.085. Yes, we get 234. Okay, this is correct. Okay, this is correct. So now this is correct value, correct value, correct value. So the last point will be here. Okay, first point is 0, and then this is the third point, fourth point. Okay, like this. This is number 1, this is number 2, this is number 3, this is number 4, this is number 5 for the BMD. So, okay, 1, 2, 3, 4. Okay. So this is bending moment diagram for C and D. Okay. Okay, this is how we analyze the maximum moment in bending moment diagram. Okay, so that's all for this session. We will continue again in the next session. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.